Hello and welcome back to Precalculus. Today on the menu we have 3.3 properties of logarithms, logarithmic functions as well. And it's a very short section that introduces us to a few formulas that you will be using in your next two sections, and then also in calculus later on when you do something like logarithmic differentiation and things like that. So these properties are very, very important. And as I said, it's only three formulas here. We already looked at some basic properties before. So I'm just going to list those so you have them all in one spot, and then we're going to learn the three new properties. So I'm going to start with the most important thing of all, and that is conversion between the exponential world and logarithmic world, because without that one you can't solve any equations, and right, the whole story will be pointless. Then you might be also interested in these special, right? So log of x means log base 10 of x, and log base, ln, let's write it, ln x means log base e of x. So these are the two kind of special logs that have the special notation. They still belong to the basic logs. All of the properties and rules, right, hold for them as well. It's just that, right, we use them so much that we have special notation for them. Then we have our change of base formula that you can use your calculator to compute any logs. In general, calculators can only compute log base e or log base 10. Sometimes calculators can even do just one of those two, not even both are programmed. And very rarely you will run into a calculator that can do any base. But that's okay, because we can convert the base, right, into log b over log a, or ln b over ln a, whatever buttons your calculator has. Finally, we have those simple rules, right, where it says that the log of any base of 1 is always equal to 0. Log of any base of the same number is equal to 1. And then we have these two rules which tell us about the fact that the logs and exponential function, logarithmic function and exponential function, are inverses of each other. So if you have log base a of a raised to the x will be x, and if you have a raised to the log base a of x, you will also get nx. So these are all of the formulas and all of the concepts we did so far. And now our job is to just learn the last three formulas. And believe it or not, that's it for logs. There's nothing else to learn. Just, shovel some problems around. The next section, 3.4, is on equations, and 3.5 is application of those equations, which are word problems. All right, so what are we learning today? We are learning these three formulas. Number one says that log of any base of a product is equal to log of, addition or sum of two logs. So multiplication is of values in the argument is broken down as addition of two logs. Then, number two, you have that the log base a of division, right, common sense over here, would be to subtract if the upper one with the multiplication was adding. And number three, if you have log of any base of x raised to the power p, that power p can jump in front of the log. And these three formulas are the important formulas which we use to do all of the stuff that we need to in regards to equations and in regards to later on logarithmic differentiation in calculus 1, right? Once you reach those all the way in the end of chapter 3. Now, why do we want to know this? Well, as you are going to see in 3.4 later on, your job is to compress these logs into a single log so that you can use the conversion to solve the equation. So your job is going to first be to practice these equations here, to learn how to either compress or expand logs. So compression of logs would be used in pre-calculus, and expansion of logs will be used in calculus. So you need to know both, except one of them you get to use now in pre-calc, and the other one you will be using in calculus. So you should learn both immediately. Now, what do I mean by compress logs or expand logs? So you can say compress, you can say condense, you can say combine, whatever one of those words, meaning put multiples into a single, right? Combine, how about that? Combine. So you have your log base 2 of, let's say, x cubed plus log base 2 of x squared plus 1 and minus log base 2 of just, let's say, x. So what we do here is we say, by the rule 1 up there, when I have addition of two logs of the same base, they can condense, compress, or combine into a log which multiplies the arguments, the things that are in the log. Right? So these two, so these two will immediately become log 2 of x cubed times x squared plus 1. And then you still have to subtract this. Now that will be the division, which is our rule 2. So log base 2 of x cubed, x squared plus 1 divided by x. And now you see that you can simplify, right? You can cancel one of these x's. So log 2 of x squared plus 1 would be the answer in this case. So we started with three logs, three separate terms, right? Three separate logs. And we were able to condense all of this into a single log. So this is the only skill that you need to know to solve 3.4 equations. I mean, there is conversion, a lot of other things, but I mean, the only thing from this lecture you need to know to solve those equations in 3.4 and also eventually maybe word problems as well. Let's take a look at a problem from homework from this category of combining or condensing logs. So use properties to condense each logarithmic expression. So they like to use the word condense.
Why don't you just, sorry to interrupt, why don't you distribute the x squared?
Well, we like factored forms better because you can easily solve them if they're equal to 0, right? When you have x squared and then x squared plus 1 equal to 0, then you can use the zero product rule to set each one to 0 quickly and solve it. If you had this in the form like this, you can't really solve this. You have to factor it first, but then that brings you back here. So why do the double work? Generally, when you are dealing with these introductory concepts, they are heavily built upon later. And we always like to leave the answers in the factored form, because if there are equations to be solved later, those equations like the factored form, because you can set each individual factor to 0. So that's the reason.
Gotcha.
Right. So let's take a look at problem 55. Combine, condense, combine, I don't care what the word, doesn't matter. 5 ln x, that's a 5 ln x minus 2 ln y. Okay. So in order for us to combine these, we have to get rid of the constants in front, right? Because you can only combine, as you can see, these guys that have no numbers in front. Well, luckily, you can use rule 3 to get rid of the constant in front by putting it in as the exponent of your argument. So this becomes ln x to the 5 minus ln y squared. And at this point, right, it's a subtraction, so you can combine this into single ln. Right, these are all logs, L's, whatever way you want to write them. So we have ln of x to the 5 divided by y squared, and we're done. So we use the rule 3, and then we used rule 2 to get these values condensed. Like that's it. I hope you're not disappointed, because that's it. Let's see what else can we master over here. You can take a look at one of these spicier examples, like 66. 1/3 log base 4 of x minus log 4 of y, close parenthesis, plus 2 log base 4 of x plus 1. So combine this into a single log. Let's see what you get.
Are we allowed to do one of the rules to only one side of the function?
Well, this is all one side of the function. I'm not sure what do you mean, because this is all one side and then you put equal and you go to the next line, which is still one side. Now the logs will combine, right? You combine the first two logs using PEMDAS because it's in parentheses, and then you will be able to combine everything together at the end.
Okay.
So try for another minute or so, and then I will work this out in detail, so you will all get to see the result at the end. Okay, let's take a look at this problem together. So first, we combine the logs inside the parentheses by PEMDAS. That's 1/3 log base 4 of x divided by y. And we still have plus 2 log of x plus 1. Now we have to get rid of these numbers in front of the logs so we can combine the last two logs into a single log. So our goal is to condense everything into a single log. So that's going to be log base 4, and you can put this as a cube root of x divided by y plus log of log base 4, oops, I forgot the 4 there, x plus 1 squared, right? So this is the rule number 3, where you get those numbers in front of the log and you put them in as numbers in front of the log, and you put them in as your exponents of the argument. Argument is what we call the values that are inside the log. Just same like later on in trigonometry, when you say sine of x, that x is called the argument. The same thing for square roots, right? Whatever is under the square root is called the argument of the square root. So now,
So
yes,
that one you just squared, the argument would be x plus 1.
it's x squared. Yeah, x plus 1. Yes. So
Okay.
that's whatever is inside the log. That's what's called the argument. All right. So now we have these two, and it's addition. So all I need to do is to combine this into a single log base 4, where I just multiply these two together, and you can write them in any order you want, right? So you can do cube root x over y times x plus 1 squared, and that's it. So we condensed everything into a single log. So that's the skill that we need to have to combine multiple logs into a single log. Now, there are also, later on for calculus, what's important, and you will have this also on your homework. For calculus, you will have to be able to break logs apart. So let's say problem 24, right? Expand. And they give you a single log base 5 of square root of x divided by 25. So this is one of the basic, right, basic problems. And you immediately say, oh, there's a division, right? So by the formula we learned, the division, number 2, line number 2, right? Division goes into subtraction of two logs. Oh, okay. So this has to be log base 5, you have to keep the base, of the square root of x, and then minus log base 5 of 25. Now this computes further because you have this x, square root of x is x to the half, right? So you can kick that exponent out. Now there is also a really clever thing you can do here. You can write 25 as 5 squared. I hope you see that. So I'm just going to write that in the next step. X to the 1/2 minus log base 5 of 5 squared. And now by rule 3, 1/2 gets kicked outside. You have log 5 of x minus 2 gets kicked outside, and you have log 5 of 5. So the first one you can't do anything with, but the second one, this is equal to 1. That's one of the cute formulas we had. So this is just minus 2, and the problem is done. So I hope this made some sense. And as I said, this will be heavily used in your calculus for something that is known as the logarithmic differentiation, which you will need to learn in chapter 3 so you can move on, right? Let's do another one of these. And
Wait,
yep.
Isn't it when you have log 5, 25 is like 5 to what power equals 25, right?
Yeah, which was 2. But
Five.
see, if you rewrite 25 as
Oh,
5
okay, I see
squared,
now.
the 2 goes in front, so it makes it nice.
I'm confused on the last step where you went from -2 log 5 of 5 to just -2. Where did that log 5 of 5 go?
It's 1. That was the formula from the last class.
Oh, okay. Oh, I missed the last class. That's probably why I'm confused. Never mind.
Okay. So now let's take a look at another one of these. They have like a ton of these. Here, problem 36 looks awful, which is exactly what we like, right? Log base 2 of the 5th root of xy to the 4th divided by 16. Let's see what you can master on this one. So again, try for 1 or 2 minutes, and then I'll kick in to see if you...
We're expanding this one, right?
Yes, it's a single log, so expand. If you have multiple logs, then you want to condense them.
I think I get all of them except the first like thing that we do. How are we going to get rid of that root 5?
Well, isn't that the root 5 the exponent on the entire expression? The entire
Yeah.
argument, okay. And how do you get rid of the exponents? Which rule out of the 3 is the one that gets rid of the
Is it rule
exponent?
3?
Rule 3, very good. So we
Oh,
start with rule 3, then we move
am I
into...
going to take it out and put it as like a coefficient?
Yes, very good.
Okay.
So technically, you mastered this. If you see that,
I don't know about that.
well, that's it. I mean, there is nothing else. Those 3 rules are the only 3 rules, right? And eventually, if you end up having like the same numbers to cancel again, which in this case you will, but yeah, that's it. So we're going to start with rule 3, and then we're going to go into rule 2, rule 1, and see if we can simplify anything.
When I get rid of that root 5 and I put the coefficient in front, and then I split it because I'm subtracting because of the division sign, am I putting the coefficient 5 in front of...
What 5? It's not a 5.
It's not
Nope.
to get rid of the root?
What's the exponent for the root? To have a 5th root, what's the exponent?
It's 1/5.
1/5, yes.
Ah, damn it.
Right? So it's 1/5 for roots, because when it's a 5th power, it's a 5th power. But the root is 1/5. So that kicks out 1/5, and then you have your log base 2 of this xy to the 4th divided by 16. So now you get to divide this further.
think I jumped up a couple steps too early. I tried to do the subtraction before I.
Right, so we're going to do subtraction now. And this 1/5 will multiply everything. And so we'll open parenthesis because 1/5 needs to multiply everything. So that's going to be log base 2 of xy to the 4th minus log base 2 of 16. 1/5. Now we have log base 2 of x plus log base 2 of y to the 4th minus log base 2 of 2 to the 4. So 16 can be written as 2 to the 4. And this is where you kick all of your exponents in front. Well, log 2 of x has nothing, plus 4 log 2 of y, and minus 4. Right? We know that log 2 will give us 1, so we don't have to write that one. That's it. It doesn't cancel. It's just log 2 of 2 is 1, so 4 times 1 is 4. So it didn't cancel. It's 1. That's it. That's for 3.3.
We try another one of these.
Technically, it just sets us up for 3.4. Sure. Let's see. Problem 34 looks cool enough. I can do 34. Why not? Log base b of cube root of x times y to the y to the 4th is separate. Good. And then z to the 5 on the bottom. There we go. So what is the first rule that needs to be used for this?
The whichever one was the division and subtraction one. Log or rule 2.
Yes, rule 2, division and subtraction is the first one. And then we have rule 1 to break up multiplication. And finally, we have rule 3 to get rid of all of the exponents. So in the end, we only have like ln of x, ln of y, ln of z, right? Log base b, not ln. Okay, so we're going to start this problem by using rule 2. That's log base b of cube root of x y to the 4th minus log b of z to the 5. And then we need to break the multiplication. So that's going to be log base b of cube root of x plus log base b of y to the 4th, and then minus log base b of z to the 5. Now you can immediately write this cube root as 1/3 over here and just kick them all out. You're done. Here is the log b of x plus 4 log base b of y minus 5 log base b of z. So this is considered as fully expanded, right? Because all of your logs have this single xyz single variable, right? You don't have them combined in any way. You don't have any exponents on them. So we go all the way down to the base variable. And once you have that, then you know that your expansion was done and complete. There is one thing that I want to mention here at the end. It is usual tripping point for students when you have two factors in the denominator. Each one gets a minus, even though they're multiplied. They're both in denominator. So I don't know at which point algebra fails to the point that that's not realized. But let's say you have ln of, I don't know, 3x divided by xy squared. Yz squared. Because if it was x, you just cancel it. Right? So you will have your ln 3x for the top, but then you will have minus ln y and minus ln z squared. This is also minus because it's also divided by z. Students would usually argue, but it's multiplication here. Yes, it is multiplication there, but it's a multiplication in the denominator, which makes it a division. Because when you have 12 and you divide 12 by 3 times 4, what's the answer? Right? The answer is you divide 12 by 3, which gives you 4, and then you divide that by 4, and then you get 1. Which is, if you do the multiplication, you will get 12 divided by 12 gives you 1. Right? So when you have multiple ones in the denominator, right, you will have each one of them get its own minus sign. And then if you want to break this apart, like ln 3 plus ln x minus ln y minus 2 ln z. So this is just a side note because, you know, when it shows up, especially when it shows up in calculus, and I did mention that this type of expansions you will need for calculus. The first part we covered, which is the compressions, right, condensing into a single log, that's needed for our next section 3.4, where we do exponential and logarithmic equations. So any questions, concerns about these log compressions and expansions?
Can I just see the solution of the last one real quick? I didn't get a chance to write it down.
Is it I'm not sure which one, but here are both.
No, yeah, that one right there.
So we'll take about 2-3 minutes break for me to switch out the titles and things, and then we're going to jump in 3.4, right, to learn about equations and use that conversion back and forth to solve logarithmic and exponential equations. So see you all very soon.